And then because oftentimes they might ask you to approximate more than one thing, it's good to go ahead and get this in its simplest algebraic form. You might be using it over and over again. Most of them, maybe not, but it's good practice. So you would have -4 times x, -4 times -2, that's another 8. So you have 16 minus 4x. Is that right?
Yeah.
I'll just write it the usual way though. Write mx plus b form. So L of x equals -4x plus 16. So what we really found, ultimately, was the tangent line to this curve at that location, right? Our linear approximator is simply the tangent line at that location. You guys with me on that? That's all she is.
Can you point on the drawing what you meant by that?
This equation, -4x plus
Yeah.
16, is this red line.
Oh, the
We
whole.
found the tangent line at that location. Correct. It's always going to be on the tangent line. That's what you're always finding. Just calling it something different. It's calling it our linear approximator now. But it's the tangent lines that you guys constructed, for better or for worse, on previous exams and previous homework problems. So now, part B. Graph the function and the linear approximation near x equals a. So I got to draw both these pictures. So I'm glad I picked 12 minus x squared. It's not so bad, right? Draw both of these things. 12 minus x squared is simply a downwards opening parabola moved up 12 units, correct? Standard parabola, opening downwards, moved up 12 units. So if that's, I should do some good units. So 2, 4, 6, 8, 10, 12. What are its roots? Stupid 12. What is it? 2 root 3 or something?
I think so.
2 root 3, -2 root 3, right? Ah, stupid numbers. So 2, 4, 6, 8, 10, 12. So 2 root 3 is approximately what? 3 something?
What are you asking for?
What's 2 root 3? I know. I just want to draw a reasonable picture for this curve. So if I find its x-intercepts, that will help me. Its x-intercepts
3.4.
3.4. Okay, that's all I need. 3.4. Just to have some reasonable picture here.
3.5 actually.
Okay, so sorry, in here somewhere, right? These are all 2s, -2. So somewhere in here. Okay, it's not over far enough. I'd like to be somewhat reasonable. Okay. There's the original function. F of x equals 12 minus x squared. We're supposed to draw the linear approximator to that function. -4x plus 16. Remember that in my particular picture, I've used scale 2. So first of all, where are we drawing this picture? At 2. So at 2, when you come up here to the curve, right? There's our location up there. And there should be a tangent line whose y-intercept would be 16, so that's 12, so 14, 16. So it's got to go through there. Right. Just draw it something like that. Okay? That has a perfect -4 slope. Raja disagrees. Whatever. Okay, so there's our linear approximator. There's L of x. 16. Everybody understand the picture? How we created it?
So what is this showing us? We just
It is showing us not only the original function we started with, but the tangent line at 2. The tangent line at 2 is our linear approximation for x values around 2.
Okay.
So now if I pick an x value which is around 2, like say 2.1, I think is what the question actually asked, then at 2.1, I'm going to plug that into this expression, the approximator. I'll get out a value which is close, hopefully, to the actual expression if I put in 2.1 into here. And it seems reasonable, especially how thick the considering how thick the exponent markers are. This is like all right on that curve, right?
If you find approximation, you have to take second and third.
Now remember, the second does not tell you how far off it is. it tells you to expect you should be off by more or less. That's all it tells you. It does not actually tell you the error. It doesn't tell you how much you are.
Oh,
The second error doesn't tell you how far off you are. It tells you to expect how bad an approximate it is, depending on how sharp the curvature is. Okay, so let's just do the next part of the question. Hold on a second, Justin. Yeah.
Okay, can you just quickly explain how you get the x minus a equals x minus 2 on the left half? Really quick?
Yeah, I was just writing out this last piece here. For now, she wanted me to like write all the pieces out for the linear approximation.
Okay.
So it's always x minus quantity, and that quantity came from here. That's all.
Oh,
So x minus
okay.
2. That's all it is.
Okay.
So they tell us to now approximate, use the linear approximation to estimate the given function value. The given function value they want is f of 2.1. So approximate f of 2.1. So we're going to put 2.1 into our tangent line, right? That is our linear approximation. So approximate f of 2.1, we will take L of 2.1. Just plug that in. We'll get negative 4 times 2.1 plus 16. So we get negative 8.4 plus 16 equals what? 7.6? 7.6. 7.6. There's our guess for the height of the original function, for this height, at 2.1. Okay? That's what we found. And we anticipate it's an overestimate, right? Because we have a concave down function. All the tangent lines lie above, so this should be an overestimate for the actual.
So the linear approximation of f of x at a equals 2 is the same as the tangent line as a equals 2. That's all.
Correct.
The first part.
That's what you want to. That's what you want to understand. Yeah, it is the same as the tangent line.
Okay.
What you're now doing, though, you didn't do before, is you're taking other values around where you found the tangent line. You're taking other values around there, and you're plugging them into the tangent line, and you're getting points on the tangent line, which are close to the points on the curve.
So is there any reason why we use that formula instead of just saying, like, find the equation of the tangent line, then plug this new value into it?
Not particularly.
Okay.
That's all that is. That is the tangent line. That's why I wrote it like this, right? I finished it off by writing it in full mx plus b form. It's always going to be like that. Always going to be a tangent line. Compare the percent error in your approximations. Okay? So percent error instead of actual error. What is percent error? Percent error. Percent error is actual minus approximate over actual times 100.